Hello and welcome everybody to Astronomy Days. We're here back for another exciting program, bringing you exciting topics, interesting guest speakers, all on subjects surrounding space, astronomy, astrophysics. We've had an incredible week's worth of programs talking about space and asteroids and spacecraft. And this next presentation is going to be no different. I think you're really going to enjoy this one. It's very topical. Of course, we're going to be talking a little bit about the James Webb Space Telescope, which has been all over the news, has certainly been dominating my Twitter feed lately, and is such an exciting step in astrophysics and in exploring space. So glad that you're here with us. Briefly, I'm going to go over a quick tutorial on how everyone can use the Zoom platform if that's where you're joining us, because we want everybody to be able to take advantage of the chat for asking questions and leaving your comments, as well as taking advantage of the accessibility features that we have available to you. So quickly, everybody will have their audio and video already turned off, but if for some reason it's not, go down in the bottom left-hand corner of your screen and make sure that your camera and your microphone are turned off for us. And then in the bottom middle of your screen, you'll see a button for closed captions. We do have live captioning available to you. Click that button and then click show subtitles. If you need to, you can adjust the settings for the subtitles as well so that you can get the best experience possible. And we recommend that you watch today's program on Zoom in speaker view. Then click view options and switch it to side-by-side mode. That way you've got the presentation and the great visuals with our guest speaker on camera all at once, all on your screen, no distractions for the best experience possible. Now, as we go throughout our program, when questions about the topic pop into your brain, pop them into the chat box as well. We have moderators who are watching the chat on Zoom and over on YouTube where we're live streaming. They're going to be collecting those questions and dropping them into the chat where I can see them so that after the presentation, we'll be able to pose your questions to today's guest speaker. And also, really special, really cool, I think we've got extra special moderators hanging out in the chat. So if you see them pop up, just be like, hey, cool person, thanks for joining us. And that is how today's program is going to go. So without further ado, I think we should jump right into such a special program that we have today. And to get things started, to kick it off, we have a very special guest. Congresswoman Deborah Ross is with us today. Congresswoman Ross represents District 2 here in North Carolina, which is Wake County, and joins us now. Welcome.
Well, thank you so much, Chris. And I'm so excited to be joining you for this discussion about the James Webb Telescope. As a member of the House Science, Space, and Technology Committee, I'm deeply committed to ensuring that we advance American leadership in scientific innovation by making bold investments to help us better understand space. One of the most vital recent investments we've made toward achieving this goal was the launch of the James Webb Space Telescope last month. The telescope celebrates the life and legacy of former NASA administrator and North Carolina native James Webb, whose vision and tenure were integral to ensuring our country's institutional support of space for generations to come. When President John F. Kennedy launched a new era of space exploration by announcing his goal of landing an American on the moon before the end of the 1960s, it was Webb who was charged with fulfilling that historic mission. He oversaw the Apollo program and laid the groundwork for Neil Armstrong's famous giant leap for mankind in 1969. And I'm old enough to have remembered that. Now, the telescope that bears his name has embarked on a historic mission of its own that will allow us to continue making groundbreaking discoveries in space. It's a privilege to share the virtual stage with Dr. Stephanie Milam, who will share her experience working on the James Webb Space Telescope and offer insights into what we might expect from Webb in the months and years ahead. Now that the telescope has reached its final destination, I share the excitement and anticipation of all Americans to learn about the secrets that Webb will uncover about the universe. The James Webb Space Telescope was made possible because of the ingenuity of American engineers and scientists like Dr. Milam. They learn, discover, and innovate every day. We must continue our support of STEM research and education so we can advance the James Webb vision of American excellence in space. And I want to close by thanking the North Carolina Museum of Natural Sciences for hosting us. The work you do to educate and inspire North Carolinians, especially our youth, is vital to the future of our state and our country. This past week's astronomy days are a clear example of your mission, and I'm honored to be with you today as a part of this important event. Thank you so much, and I'll turn the program back over to Chris.
Thank you so much for being here and for sharing with us. I only recently learned about James Webb being a North Carolinian, and there's so much pride in that. First in flight and now doing so much in space as well. Thanks for being here. Now, let me introduce the person who's going to introduce our special guest speaker. If you've been hanging out with our Astronomy Days programs, then you have maybe heard a presentation from Dr. Rachel Smith or seen Dr. Smith show up in some of these other talks. The head of the Astronomy and Astrophysics Research Lab and a professor at Appalachian State. Everybody welcome Dr. Rachel Smith.
Thank you, Chris. And thank you, Congresswoman Ross. It was so great to have you and hear your remarks. And thank you for your support of everything you're doing. And I'm excited to introduce my friend and colleague, as well as JWST scientist, Stephanie Milam. Dr. Milam is a planetary scientist at NASA's Goddard Space Flight Center, which is in Greenbelt, Maryland, where a lot of amazing astronomers reside and work. And she serves as the James Webb Space Telescope Deputy Project Scientist for Planetary Science. Her background is in chemistry as well as astrophysics. She got her bachelor's in chemistry from Kansas Wesleyan University and her PhD in chemistry at the University of Arizona in Tucson, and did a postdoc at NASA Ames Research Center on interstellar ice. She is, Dr. Milam works in the astrochemistry laboratory at NASA Goddard, doing these amazing experiments related to star formation and planetary disks and planet formation. And she also has a renowned observational program with many types of telescopes, and most recently JWST. And so I think that's all I'm going to say, just to give Stephanie the floor. And thank you, Stephanie, so much for joining us and doing this talk for us today.
Thank you so much, Rachel, Congressman Ross, and Chris, for the warm welcome and for having me and letting me present to you today about the next greatest thing that NASA has just set out to reach new discoveries. Let's figure out sharing my screen. So I have a presentation here today for you. I'm going to talk a bit about James Webb Space Telescope. I'll talk about some of the science that the mission's been designed around, and some of the hopeful goals that we have to achieve with this mission. But then I'm also going to talk to you about the complexity that we have in building such a large space-based telescope, and some of the recent successes that we've had. Please feel free to follow along on social media. You'll find updates daily, sometimes hourly, depending on what's going on with the mission. So I have our Twitter and Instagram link down there, and I'm also on Twitter if you're interested. I will also say that Peter Sui, who is one of our outreach personnel for the James Webb Space Telescope, is online. He's listed as James Webb Space Telescope. So he's going to help me answer questions in real time in the chat. So either on the Zoom chat or the YouTube channel. So please, if you have questions, know that he's there and an expert here to address your questions. I want to start with the story of how the James Webb Space Telescope came to be. And it actually started with the Hubble Space Telescope. So the Hubble Space Telescope is an optical UV telescope. So it sees light that you see at optical wavelengths, but it also sees a bit into the ultraviolet and a bit into the near infrared. This telescope was designed to study astrophysics, phenomenon, including galaxies, stars, planets, planets in our own solar system, because at the time HST was launched, exoplanets or planets around other stars were not known. Additionally, we didn't know the capability of the Hubble Space Telescope when we launched it. So what you're seeing here is actually a video peering into one of the deepest exposures that we've had with the Hubble Space Telescope. We basically took a blank piece of sky about the size of a postage stamp near the moon, and we stared for hundreds of hours. And what we found was not only could we see the farthest galaxies in the universe that we weren't expecting to see with the Hubble Space Telescope, but we also saw that they actually change as you go deeper and deeper into space or further back in time. This was something that we didn't expect Hubble was able to do, and it actually led to the formation and formulation of the James Webb Space Telescope. We knew that we wanted to look back even further and see how far and how close we could actually approach observing the first stars and the first galaxies that formed after the Big Bang. So this kind of gives you a timeline of what I'm talking about. So as you were looking through that simulation of an actual observation, you were seeing that galaxies are flying by you. And that's basically as we were moving from the current modern universe back in time. And so what you can see here is how far the Hubble Space Telescope was able to actually peer into the universe. And so what we knew at that time was to look back further, we had to have a more sensitive telescope at even longer wavelengths. And I'll explain a little bit about why we needed longer wavelengths in just a moment. But you'll see that James Webb now has the capability, or we designed it to have the capability to actually look way back to the first stars and galaxies, past the cosmic microwave background, past the Big Bang, and just beyond the era of the Dark Age. So this is going to be the next step in understanding how we got here, how galaxies form, how stars form, and even how planets form. So exploring the universe with JWST, we knew having a space-based telescope to look back in time would enable all kinds of different science. But we also wanted to make sure that that telescope was capable of doing science across astrophysics and planetary science. We now know that planets exist around other stars, and that's something we're very, very interested in, especially in the field of planetary science and even in astrophysics. We want to know what these planets are made of, whether or not they could look like Earth or other planets on our own solar system. We also want to know how stars are formed. We want to know how planets are formed. We want to know how galaxies evolve. So I'm going to talk a little bit about some of these science goals that we have with the James Webb Space Telescope. But first, I want to talk a little bit about why it's an infrared telescope. So we're looking at longer wavelengths than what we can see with our own eyes. Think about it as night vision goggles. So we're seeing things that are warm in the early universe. So to see these warm things, we have to go to longer wavelengths. Additionally, just because it's warm doesn't mean it's not necessarily the same kind of star emitting the same kind of light that our sun does. These stars and galaxies actually emit light at UV and visible wavelengths the same way the sun does. But because they're so far away and it takes so long for that light to actually come to us, and the universe is even expanding, to throw that on top of there, the light is actually stretched to longer wavelengths. So we have to go into the infrared to actually see light, like our sun, as it approaches us. And it's actually billions of years old. So we're basically looking back in time to when these first stars and galaxies actually formed. And this is what is called the cosmological redshift. And this is why we have an infrared telescope. Thinking about this, as we were going through that first video, I don't know if you noticed or not, but the galaxies actually went from very structured, some of them were spiraled, some of them look like halos, some of them look like little sombreros. But as we went further and further and back in time, you notice that we didn't have that beautiful structure that we see in galaxies that are closer in our nearby universe. So by going further and further back, we're going to be able to study how these structures actually started forming. We're going to understand how old they are and when structure actually started coming into play. We have the resolution to really start seeing when they went from these blobby sort of globules in the universe to something that looks like a spiral galaxy or the Milky Way today. So just because they're less structured doesn't mean they're not interesting. It actually might have meant that we just didn't have the resolution to see whether or not they had structure. So that's something that James Webb Space Telescope will have, that, and with that resolution and sensitivity, hopefully we can pull out whether or not they did have that and or when it actually evolved. So this is one of the main primary goals of why we have the James Webb Space Telescope, why it is an infrared telescope, and why it is so extremely big, just so we can see these first stars and galaxies. But one of the other really cool topics that the James Webb Space Telescope is actually going to help us understand more about in astrophysics is black holes. This is a question I get at almost every public talk I've ever given on James Webb Space Telescope. So I like to highlight the science and the capability of it, even though I'm not an expert by any means in black hole science. The Webb's going to peer into the obscuring dust to study the center of our own galaxy, where we have our own black hole known as Sagittarius A. And we're going to follow the stars that are actually orbiting that black hole and study what the dynamics are, what the temperature is, and what the composition is that's being altered or affected by the central black hole. We'll take high resolution spectra to study about all of these different physical parameters and understand how they've formed and altered our own black hole, and then study other galaxies in the nearby universe to see if their black holes are contributing to the same kind of phenomenon. We can also help address broader questions of how galaxies form, including the long-standing problem of which came first, the galaxy or the black hole. Another fun topic is actually having the infrared capability. We can actually see through clouds. So the same way clouds in our own sky obscure light or anything beyond our Earth's atmosphere, we have clouds in our universe where stars and planets are actually being formed. These clouds are huge structures. They're way bigger than galaxies. It's actually where new stars and planets are actually being born. It's the dust and the gas that is actually forming the whole system, the whole mass and clump that eventually forms a planetary system. Hubble Space Telescope didn't have the capability to study what was inside of these clouds because, like our own eyes, it could not see through the dust, through the gas of these giant clouds in space. But with the James Webb Space Telescope, with its night vision goggles, we'll be able to see inside of these clouds and even objects behind them, so we can study what's going on within them and really studying that stellar nursery, where stars are born, understanding how planets are formed, and how the whole mechanism is actually at play. Finally, with planets around other stars, we had to determine how we could actually study them with this really sensitive telescope designed to study the first stars and galaxies across the universe. So one way to do that is actually to block the light that we can actually observe with this really sensitive telescope. And we do that with a mechanism that we basically put a sort of sunglasses, or you can think about shading your own eye or covering one eye so something isn't as bright in front of a star. And that helps you see all the fainter objects that are around that star. And this is one way that you can actually image planets around other stars. And it's a capability that the James Webb Space Telescope will have, so that we can actually study the planets in their own systems. The other way we like to study planets is through transit spectroscopy. So this is when we have an occultation, or you can think of whenever the moon goes in front of the sun, or when the Earth and the moon has its own blockage, we have the same phenomenon that actually happens in space. So what happens is a planet will cross in front of its star, And when it does this, we can see the brightness of the star actually drop because it's being shaded by its own planet. Bigger planets have bigger shade, and so we can actually study how big a planet is, what its orbit looks like, and even more importantly, we can study what the composition of the atmosphere of that planet is. So this is an actual spectra that's taken of the Earth's atmosphere. And what you can see are all the key ingredients for Earth. And so what we want to do is look for other planets and around other stars and see if they have a spectra that looks like Earth's. This will give us insight into whether or not there's some sort of process happening on that planet altering the atmosphere in some way, be it geologic process, so think of something like volcanoes or dust storms, or whether or not it's something like life or biology, where it can produce really essential things that we actually need to have living organisms. So key ingredients that we're going to be looking for in these planets are things like water, carbon monoxide, carbon dioxide, methane, and other essential molecules that will really give us and provoke the idea of some process happening in that planetary atmosphere. But of course, I have to talk about the bread and butter of the James Webb Space Telescope, my science, which is science within our own solar system. Now, we have a funny shaped telescope, which really inhibits what we can observe within our solar system. We can't point the telescope towards the sun, and we're in an orbit just beyond Earth. So basically that limits the capability of observing anything within the solar system. So we're kind of restricted to Mars on outward. But this is okay. It also includes things like near-Earth asteroids, comets, and all the small bodies in the inner and outer solar system. So we have a lot of science that we can actually do within our solar system with the James Webb Space Telescope. In fact, this is a summary of all of the programs that are going to be happening in the first year for our own solar system with the James Webb Space Telescope. We have programs that include things like comets, interstellar objects, Mars, asteroids, moons around Jupiter, the rings of Saturn and its moons, including the two most famous ones, Enceladus and Titan. We'll be looking at the ice giants. We'll be looking at the outer solar system, including Pluto, and all the other small bodies in the outer solar system. One of my favorite topics, though, is actually studying ocean worlds in our solar system. So there are a number of satellites now that have been discovered to have sort of plumes of water or gas coming out of these icy, crusty surfaces. So one example of that is Europa, which is one of the large moons of Jupiter. Hubble Space Telescope actually observed water vapor coming through the surface of this satellite. Well, James Webb Space Telescope has not only impeccable resolution, but we have spectral capability that we can actually map across the surface of this particular satellite. And each one of these little squares, which is resembling one of our science instruments, has a full spectrum, which you can see on the right, where we can actually not only map across the surface of the satellite itself and see whether or not there's volcanic deposit on the surface. So you can think of, lava that actually forms this different composition across the surface of Earth once it comes out. These plumes of gas might actually refreeze onto the surface and give us some evidence of what's going on. But also we can study the plumes themselves. And this is one of the projects we hope to do within the first year of James Webb. But with this sensitivity, we also have access to the outer solar system, which is something that we haven't really been able to do a lot of exploration, especially in large numbers at least, the way that we would really like to. So we can better understand how planets formed, what the fate of our solar system was in its early days and how it's going to evolve, and how planets and other systems are actually being formed and evolve. So we have the sensitivity with the James Webb Space Telescope to actually characterize, basically understand what they're made of every single one of these small bodies in the outer solar system that exists sort of beyond the Neptune region. This is where Pluto resides, as well as a number of minor planets, as well as a lot of interesting objects that we just don't really know much about. So I'm going to use Pluto as the #1 example because Pluto is our favorite minor planet slash whatever you think it should be. Even astronomers can't agree on what Pluto is today. So this is an image that was acquired with the New Horizons mission. And it is a spectacular image of Pluto. We have the wonderful heart of Pluto. We have these dark areas. We have really bright areas. So while JWST is not going to see Pluto in the same way New Horizons did, because we're nowhere near as close as New Horizons was, it will see Pluto in the same vein that the Hubble Space Telescope did. So this was the Hubble images of Pluto right before the New Horizons mission actually got to it. And what you can see are dark and light spots. We can even see the heart of Pluto if you look at the center image there. So James Webb will have the capability to get the same sort of resolution across the surface of Pluto, but we actually will have better spectroscopy so that we can actually do the same sort of studies that the New Horizons mission did, as is the case that I'm showing you here, where New Horizons was able to map methane across the surface of Pluto. And you can see in the brighter area, in the green area, the spectra looks very, very different from the red area. And so with James Webb Space Telescope, we have spectral capability where we can go across the entire surface and study what the composition is, how it varies, whether or not it depends on where Pluto is within the system. But we also have access to the other side of Pluto, which New Horizons was not able to image. So that was a little bit of highlights about some of the science, and I'm happy to indulge in questions after my presentation. But I want to talk a little bit about the technology. The James Webb Space Telescope is an absolute feat of engineering. And the success of this mission to date is just mind-blowing. And I have to brag a lot about what went into this to make it look so easy. So first, I'm going to talk about how big this telescope actually is. The Hubble Space Telescope has a primary mirror that's about 7 feet high, which is pretty tall compared to the average human. But if you compare that to the James Webb Space Telescope, it is absolutely minor. It's about 3 times smaller, in fact. And what you see is the 6.5 meter or over 21 foot diameter that we actually have with the James Webb Space Telescope. This is a huge mirror. In fact, it's so large that having a solid mirror like the Hubble Space Telescope was just something that we couldn't even consider, especially to launch. That much glass as a solid sphere would be, disk, would be extremely heavy and very hard for any rocket to actually launch into space, let alone to fit inside the fairing of a rocket itself. I will say, average human being is a little bit taller than me, so I consider this telescope to be ginormous. But not only do we have this huge mirror, we had to make sure the mirror was focused. So this was the one test that the Hubble Space Telescope didn't do on the ground prior to launching. We are sending the James Webb Space Telescope 1 million miles away from Earth. So we're not going to be able to send astronauts there to fix it in case anything should not work the way that we wanted. So we had to design ways to test and actually practice focusing the telescope mirror. And we do this with a technique called wavefront sensing and control. So basically what we're doing is taking the 18 segments of this mirror and making sure that they all work together and having 18 images put on top of each other so that they look like one single image, one mirror, one solid figure. One of the fun things about this is that the spinoff from this technique is actually now used for research in cataract and other eye movement procedures that are happening with LASIK procedures. So this is really a cool technology that's actually now helping out you and me, especially as I get older, for correcting your own lenses in your eyes. Telescope is complex. We have 3 main components. One is the most noticeable, the giant gold mirror, which is the optical telescope. We then have this giant sun shield, and then on the bottom of the sun shield is the spacecraft. But the heart of the telescope is what we call the Integrated Science Instrument Module, or ISIM. This houses the 4 science instruments that we have, including spectrometers and cameras. They're contributed as an international part of this program. We are joint with NASA, the European Space Agency, and the Canadian Space Agency. Our giant sun shield is also quite noticeable. And basically what we're doing is we're putting our telescope in the shade, the same way you would use a sun umbrella on the beach. We're basically putting that umbrella on the sunward side of the telescope, cooling it down to minus almost 400 degrees Fahrenheit on the cold side, and the hot side is about 185 degrees Fahrenheit. So we have an SPF with this sun shield of about 1 million, and it's also extremely large. It's the size of a regulation tennis court. And all of this is just to keep this primary gold mirror extremely cold, because we're looking for tiny little warm features across the universe of these distant galaxies, but also to help preserve the telescope and safety from radiation of the sun, the earth, and the moon. Excuse me. Oh, so the challenge we have now with putting this sun shield, this tennis court size sun shield, into a rocket, as well as our extremely large mirror, was another engineering feat that we had to face. The fairing of the rocket actually is a lot smaller in diameter than what we have. So what we had to do was fold the telescope like origami so that we can stuff it into the fairing of a rocket. This meant that we had to understand how to not only fold the telescope, but also be able to launch it successfully with working mechanisms to unfold the telescope in space and make sure everything worked properly. This in and of itself was a huge challenge. Not only do we have a huge telescope, we also had to think about things like how much it weighed. So the materials that we used in the observatory were also something to think about. Our sun shield is like a capped-on material, or you can think about happy birthday Mylar balloons with a little bit of insulation on them to make sure they were as lightweight as possible, even though they had to be so big. The mirrors were made out of beryllium, but it was sort of a bored out material to make sure that they were also lightweight. The carbon fiber structure that supports the telescope mirrors and all of the other intricate parts within it was also something that had to be extremely lightweighted, but also stable. But this is what the telescope actually looks like in its launch configuration. I had the opportunity to go and visit the telescope just before it was shipped down to French Guiana before launch. So this is my ta-da pose that we actually have a full telescope and that I actually got to see it. So how did we unfold this telescope in space? Well, it took us about a month to unfold the entire thing. We had to do it in phases and steps to ensure that the contamination of the rocket launch, including things like the atmosphere of the Earth that would have been in the fairing of the rocket, dust, or any other small particulate material, was away from the telescope and outgassed enough that it didn't freeze onto any of our surfaces and cause contamination, thereby inhibiting the sensitivity of the telescope. So first we had to basically unfold the sun shield. Once we did that, we had to isolate the telescope and the instruments from the warm side of the telescope, so it sort of popped up from the surface. Then we had to unfold the secondary mirror so that we could actually guide light into the observatory to the instruments. And then we had to unfold the wings of the mirror. This was a very complex sequence and it was very challenging. We also had to be able to move this observatory around in space, not only in space, but also move it around so that we could get to all of our test facilities and integration facilities. We did this by developing its own little transportation system. And I say little in a very laughing manner. This is actually a C5, so you can see how big this container actually is. It was a real challenge moving it around. It's definitely an oversized load on the road, which caused a lot of challenges as far as making sure the infrastructure of each city that we were actually going to was capable of holding this mass. To fly it around, I just said we had to fly it on a C5. And then we also had to ship it down to French Guiana for our launch. We had we had a special transportation vehicle that was assigned to the project. We had to go 6,900 nautical miles, or almost 20 days, from California down to French Guiana, and successfully deliver the observatory down to Ariane space to be implemented with a rocket. These are some of the final images we have of the observatory on Earth. You can see it in its beautiful launch configuration, getting installed with the fairing there on the right. We had a very successful launch on December 25th on Christmas Day. It was Christmas morning. I was sitting with my JWST mug and my JWST socks, and all of the nerves of 300 people combined, and trying to focus on a successful launch. It was beautiful, nominal, and nothing went wrong. Fantastic pictures that were taken by our team. We even had the luxury of having a camera on the fairing. So we got to see the telescope separation, and we actually even got to see the solar array deploy, which was just well above and beyond anything anyone was expecting to see on the project. The current today is 35 days past launch. All of our major deployments have been successfully completed as of January 8th. We inserted into our L2 orbit successfully on Monday, and we are now going into the next phase of commissioning, which is focusing the telescope and turning the instruments. People, ground-based astronomers, amateurs, and professionals have been tracking the James Webb Space Telescope. So this is just a little video on New Year's Eve of JWST on its journey. These videos are all over the internet, and they're so much fun to watch, even though they're just little dots. So where did we go? Well, we went to L2. So this is a gravitational saddle point of the Earth-Sun gravitational system. There's actually 5 Lagrange points, and L2 is the one that's furthest away from the sun. So it actually gives us a nice, cool area that we can actually follow the Earth around the sun and stay in a nice, stable orbit. We're in orbit around L2. We aren't in the actual stationary point. So we do have to burn fuel to stay in that position, as well as to fight the gravity or the radiation pressure, sorry, not the gravity, of the sun that's pushing on our giant solar shield. And then we also have to unload momentum. So just to point the telescope, we actually have reaction wheels. So to unload that momentum, we unfortunately have to burn fuel. This is kind of what it looks like as we go around Earth. You can see we're in this beautiful orbit. It's a large orbit. We're not in the shadow of the Earth or the moon, so we always have access to the sun, and we always have access to the Earth. We have a fantastic page that's been so much fun to follow along. It's called Where is Webb? You can see not only where it is as far as its distance from Earth and as it's in orbit, it shows you things like the temperatures, the speeds, etc. So this has been a lot of fun to follow along, and they still have updates on this page routinely. So this is where we are as far as commissioning. It takes us a long time to get this telescope ready to go. We have 6 months total from launch till we actually will see the first images and spectra that have been taken with the James Webb Space Telescope. We've finished all of our deployments. We're now starting our telescope commissioning. So this is where we're going to be focusing the telescope, making sure all of those 18 segments are properly aligned. And in the meantime, turning our instruments on so that they are getting ready to be commissioned after 120 days. Once the instruments are commissioned, we test the capability of the observatory, and then we'll start acquiring images, and science begins about 6 months. So summer of 22. So with that, I'll say new discoveries absolutely are waiting for us. I showed you some of the science that we're planning for, but I think the best science is going to come from the things that we don't even know yet. We have full capability with this observatory to study things in our solar system and out of it. So I can't wait for the next generation of astronomers to come forward with their own ideas and their own discoveries. Thank you so much for your time.
Let's give Dr. Malama a great big round of applause. Thank you so much. Let's see. We've got a few questions that have come into the chat during the presentation. I'll remind everybody that you can continue to post questions. If you're watching on YouTube, drop them in the chat. And then right here on Zoom, drop them there as well. That way we can take your questions. We can get to the bottom of what you want to know about James Webb Space Telescope. And the first question that I want to ask you, Stephanie, is a pretty interesting one. What part of the telescope are you most afraid will fail?
Let's see. Probably any of the instruments. And I say any of the instruments because they all have amazing capability. So we have 4 science instruments. 3 are actually near-infrared science instruments. One of which is a camera, which is our primary instrument. It's called NIRCam. It was built by the University of Arizona. That camera is what's going to be doing all of our extreme imaging with fantastic sensitivity, these first galaxies, as well as other capability as well. And it's our workhorse cameras to actually make sure the telescope is aligned, and we do all of our major focusing and routine activities, calibrations, and otherwise with this camera. We also have a near-infrared spectrometer, which is provided by the European Space Agency. This is our workhorse spectrometer and has extreme capabilities for detecting all of these molecules in planets around other stars, as well as within our own solar system and star-forming regions. We have a near-infrared slitless spectrograph, but it also is coupled to our fine guiding sensor. This was provided by the Canadian Space Agency. This instrument's critical. Well, the fine guiding sensor is how we actually point on objects across the universe. So we definitely need capability there. And the near-infrared slitless spectrometer is going to be our workhorse spectrometer for detecting atmospheres of planets around other stars. Then we have a mid-infrared instrument. It's our only instrument that's actively cooled, and it has capability from about 5 to 28 microns. This is our only mid-infrared instrument, and it has a camera and spectrometer. It was built by the European Space Agency, as well as some contribution from JPL. And it's our only mid-infrared instrument. So all 4 of them have unique capabilities, and I don't think we could do without any of them. At least we wouldn't be able to deliver any science.
I mean, I guess following along, everything has gone really well so far, not to jinx it. But I think the engineers and the team at NASA who put the thing together have done a pretty good job.
Yes, everything has just been what we call nominal. But as a generic on the street scientist, not scientist, I'll tell you, it's been absolutely amazing. Beyond nominal is the only phrase that I can think of. We made it look easy, and that is absolutely overstated. It was not easy. It took us years of testing and practicing how to do this. And without all of that time, energy, and routine rehearsals and working all of the mechanisms, the technology, the troubleshooting that we've done over the last few years, I don't know that we would have had nearly as successful of a launch as we've had to date.
Love it. Love it. Okay. Next one for you. Is JWST going to be involved in the search for Planet X?
I love this question. So JWST does not have the capability to do searches across large areas of the sky. And I say that because we have a really limited field of view. So what I'm saying is the amount of sky that we can observe at any given time is a very small patch of sky. We have a next generation of observatories that are coming online, including the one that's following the James Webb Space Telescope called the Roman Space Telescope, which has an extremely large field of view. So it's designed to do searches across the sky. So while we're not capable of searching with JWST, what we can do, and actually it would be the perfect observatory to actually use, is actually study the planet 9 or X or whatever you want to call it, if and when it is discovered. Even if we have an inkling of an idea of where it is, we could do some follow-up observations to help support that campaign. But doing broad sky surveys is not something that the James Webb Space Telescope is designed to do.
Excellent, excellent. All right. Will the Webb focus more on things that have already been discovered or try to find new planets, galaxies, and so on?
Primarily on things that have already been discovered, or at least suggested. There is one program that's really compelling, and it's in our nearest neighbor. So in the Alpha Centauri system, we know that a planet exists around one of the stars, but we don't know, and we have yet to detect or discover a planet in the other star. And so this is something we're really interested in, and we have reason to believe that there is either a planet there or a planet forming kind of a system. So what we plan to do at JWST, because it is so close, we don't need the extreme sensitivity to do searches in the way most people are doing for exoplanet discovery. We are planning to look at the system very carefully and try to understand what's there or what dynamic process is going on to either influence the formation of planets or absolutely destroy the presence of planets. So that's one program that's actually going to happen in the first year of observations, and it's really quite exciting. We won't be searching in general for planets or new galaxies. I imagine that there's going to be a number of these deep surveys, though, that happen to search for the first stars and galaxies. But it's a very finite area of the sky. And again, not one of these broad surveys where you can do searches for things like Planet 9.
All right. Let's see what's up here next. One of our viewers wrote, extending the mission lifespan by 10 years with the reported smooth launch seems like a surprisingly long time. Was at least some mission lifespan extension anticipated from the launch process?
So we have a formal requirement from NASA to have a 5-year science mission. So after launch, so we have 6 months of commissioning. So we had another 5 years that we were supposed to deliver to NASA as a capability. So 5 years of full operations. However, we also were required to carry 10 years worth of fuel. So we had always anticipated having or hoped to have more than a 5-year mission and actually planned on something like 10 years. But even our early simulations of the mission plan have suggested that we would have over a 10-year. Now, launching on Christmas Day with our rocket, with the perfect conditions, all things well aligned, the launch being nominal, our orbit correction being perfect, all these things falling into place just right, really gave us that edge and pushed us over the 10-year mark with a lot of confidence. They're working now on what that final number actually looks like. We're doing a couple of final sort of orbit maneuvers within L2 that will give us a better feel for what's going on in that position with the telescope fully deployed, the real life scenario. So we should be able to refine that number sometime in the very near future. But that being said, having a 20-year mission or even longer, if we're really lucky, would be the perfect thing. I always get asked about serviceability just because people are very hesitant about the idea of this fantastic observatory only lasting a decade. So having multiple for future generations of scientists to be able to, exploit the capability and have their own science is something that I, myself or the project or anybody in the world could have asked for.
Sounds like good job security for a deputy project scientist on a
perfect
telescope.
Job security.
At least 20 years.
Yeah, yeah.
Okay, let's see. We've got a viewer who's curious about the Trappist system and if and when James Webb might take a look.
The Trappist system is very compelling. So this is a planetary system and around another star that has a number of planets comparable to our own solar system as far as numbers go. And a few of those objects are actually considered to be in what we call the habitable zone. So these are planets that could have a terrestrial body with potentially liquid water on the surface, and hopefully have atmospheres that are compelling. The Trappist system is definitely in the first year of observations. This is something that's been planned since the Trappist system was discovered. We've had people that have been working on how they were going to use James Webb to look at the Trappist system. So that's very exciting results. Hopefully within the next year, I'll be able to come back and tell you all the fantastic results that came from that observation.
What's your favorite part of the telescope?
Oh, that's a hard question. I've never got that question.
How do you, that's like, you know, how do you pick your favorite pet or your favorite, you know, offspring when there's just so many great things?
Okay. My favorite part of the telescope has to be the primary mirror. There's nothing more, I mean, first of all, I'm a woman.
Sure, yeah.
It's gold, it's shiny. You know, it's absolutely beautiful. And I can honestly tell you now, having got to stand in front of the telescope and see it with my own eyes, it is so much more spectacular than any image has been able to capture, even though the images are fantastic. It is stunning. And standing just in front of the telescope and being able to look in that gold mirror, and I got to see my own reflection in the gold mirror. I don't think I have any other moment of my entire career that was more exciting or exhilarating, and I cried. Just from the mere, you know, excitement, astonishment, and just being completely overwhelmed with the success of this mission. So, and that was even before we launched. So it is absolutely fantastic. And even though it's gold and it's huge, it's not that much gold. If you condense it all down, the amount of gold on the surface of any of these, or across the entire JWST project, if you condense it down, it's only about the size of a golf ball. So it's just a very, very thin layer across the surfaces. But it was so perfectly put on there that, I mean, yeah, gold and shiny.
That's a fabulous answer. I love everything about that. All right, a few more for you. I wish I could have looked into that mirror. My goodness, that sounds amazing. Okay. Rachel has a question. Do you think we could eventually get astronauts to L2 to service this telescope if we needed to?
So the James Webb Space Telescope wasn't designed to be serviced. Once we got into a formulation part of this program, being a million miles away from Earth just seemed like well beyond the capability of human spaceflight. And it today currently is. Getting to L2 is a challenge in and of itself, but to return from L2 is an even bigger challenge, especially with humans aboard. So I think it's definitely a challenge. And I know that the private sector industry is working on these kinds of questions, and hopefully they will come up with a solution in the near future that we will be able to service facilities in the future. Whether or not the JWST will be serviceable at that point in time, or whether it's deemed as necessary. I mean, we've launched with capabilities to sustain us for a significantly long period of time. And we've only found that the rigorous test program that we put on most of our space-based facilities have durations well beyond the planned or regulated lifetimes. So I don't know that we'll need to service the James Webb Space Telescope. If we do last 20 years, if you imagine trying to service something in 20 years, what is that technology going to look like at that point in time? Is it going to be worth servicing, or is it something that will have new innovation and new technology and actually new capabilities that we need that we would rather launch instead? So it's just going to depend on where that investment comes from and what the priority and the science objective would be that you are trying to fulfill.
Excellent stuff. All right, the next question that I've got here is, with all the discussion about Lagrange points for the last few days, I wonder how big a Lagrange point is. Can you put too many things at a Lagrange point over a period of time?
That's a great question. So the Lagrange point isn't a point. It's sort of a well. So you can imagine it's not a finite position in space. It is in a region that is stable. And by stable, as I mentioned, we do still have to maintain staying within that position, mostly because of the spacecraft's structure, but also just because it isn't a finite gravitational point. Additionally, we're not at that point or near that point. We are in orbit around it. And it's a very large orbit. It's, the size of the moon's orbit around Earth. So it's extremely large. We're not talking about low Earth orbit where the space shuttle or Hubble Space Telescope would be, which is very dense, very crowded. There's a lot of debris. That's a region that would be very challenging for something as large as the James Webb Space Telescope. But being in orbit at L2, we don't have concern about that kind of inhibition, I guess, about what's there. There's a handful of spacecraft from not only NASA, but the European Space Agency and others. But being in that large of an orbit, the probability of coming even close to one of them is very, very low. There's also not a lot of debris, space debris there. We don't expect to see a lot of dust and micrometeorites or other things. It is there, but not on a level that you would expect, say, in low Earth orbit. So that's something we know it's there. We know we're going to get hit by micrometeorites and things like that. But it's not like we're going to be in an asteroid field or anything like that. I guess it's far enough, it's sparse enough, and safe enough that we're pretty confident in the safety and security of the observatory.
In a good place. It's in a good place. All right. I don't know if we know this yet. What is, or what will be, I guess, the first thing to be observed? And then if you could talk a little bit about how scientific priorities are decided.
Absolutely. So there are first observations are being planned that will be, the release to the public to say, hey, the observatory has completed commissioning. We have successfully acquired images and spectra. Here it is. Ta-da. And those are being held secret. There is a committee of scientists and individuals that work for all the agencies, as well as Space Telescope Science Institute, that have been working on the prioritization of what objects are going to be released and observed, and then that data released to the public for our early release observations. The reason they're being held close and not revealed is primarily because that list of observations is only getting refined with time. We had to have the observatory in orbit. We have to have the instruments on and the objects in the right field of view at the right time. So that list is slowly getting refined, and they'll have a finalized list, I'm guessing, in the very near future. They also had to refine that list to make sure that it didn't include targets that were part of the first year of science operations. So that gives you a little bit more limit on what observations you want to do. And they also needed to be, compelling and reveal the full capability of JWST. So it took quite a bit of thought and consideration about what objects are going to be observed. I expect nothing less than phenomenal. I'm sure we will all be breathtaking once we see them. So I'm really looking forward to it. And again, those will be released at the very end of commissioning to sort of kick off science observations. So as I mentioned, we do have our first year of science observations already planned. There is a peer review process that goes for NASA-based space-based telescopes. Even though we are a partnership with the European Space Agency and the Canadian Space Agency, operations has been given to the Space Telescope Science Institute in Baltimore, Maryland, who also operate the Hubble Space Telescope. And what they do is we release a call for proposal. So anybody in the community can propose to use the James Webb Space Telescope. You have to write a scientific proposal that's compelling to your peers and well justified, why you actually need to do these observations, why you need the James Webb Space Telescope. That goes under peer review. A panel is set up every year, and all the proposals are evaluated by the scientific panel of peers from the community and prioritized. If your proposal becomes prioritized, then you are assigned time on the observatory for that year's worth of time that's being allocated. We only allocate 1 year at a time, and it covers all topics from solar system science, exoplanet science, galactic science, and extragalactic science. So all things are considered. We even indulge in observations of new phenomenon, which can be done through what we call targeted opportunities. So you can say, I'm waiting for a supernova to happen. I don't know when it's going to happen. I don't know where it's going to happen, but if it happens, I want to observe it. And you can submit proposals like that. And again, they can also be prioritized so that you sort of have all hands on deck for something like that happening. There's also the case of things that happen that we don't know are going to happen when we submit our proposals. So let's say an interstellar object comes into the solar system, and we had no idea that interstellar objects existed. So the one way you can leverage getting time is to submit what we call a director's discretionary proposal. So the director of the observatory operations has a certain amount of time that's allocated to that person to prioritize unique phenomenon or extreme events that happen during the year of performance. So with that, we have a full year of observations already planned. That schedule is being worked as we speak. And the people that have successful proposals will know approximately when those observations are going to happen sometime in the next few months and can anxiously await for that data to be acquired.
And I guess as we wrap up today's presentation, that's kind of where we sit right now, right? Now, we've been anxious for years about getting JWST into space, and now we get to be anxious about getting the science back.
Absolutely. So once we're done with commissioning, like I said, the science begins, and that's sort of where we are with the program. One thing that will happen during commissioning is we'll understand how well the instruments are performing in space, how well the mirrors aligned, how, what it actually looks like to get data. And that will actually help us refine the mission as we go forward, because we'll now know how sensitive the instruments are, how fast we can slew the telescope if we want to track, say, a near-Earth asteroid. We'll know how extreme of objects we can actually observe. So how bright of a star can we look for planets that are orbiting around it? What can we do in our own solar system? Is Jupiter just absolutely too bright to even try to observe, or can we figure out ways to actually do things for those kinds of extremes. And so that's something that's going to be happening through commissioning, but also throughout the first year of observations. And so that's really exciting that we're only going to get better and better each year as we go on, because we'll learn more and more, not only about just science in general, astronomy and astrophysics, but also about the capability of the observatory.
Stephanie, thank you for being with us for Astronomy Days.
Thank you so much for having me. It was such an honor and it was so much fun. And I really appreciate all the amazing questions. And yeah, thank you so much for your time.
Thanks, Stephanie. And I just want to say also, it's such a busy time for you commissioning. Everyone just appreciates that Stephanie is working nonstop. So thanks for taking time for this talk.
Absolutely.
Definitely. And of course, hey, everybody, thanks for tuning in to today's presentation. We've got more coming up in just a few minutes. So make sure you head to naturalsciences.org/astrodays. Check out the remaining programs for today and programs tomorrow. Great stuff happening both days. You can also access the museum's YouTube channel to see all the programs that have happened this week so far. Take advantage of those too. And another great thing you can do is you can become a member of the museum and you can get a discount on this really cool Astronomy Days Venus themed t-shirt. Stuff like this helps support great events that we do here at the museum, like Astronomy Days, to bring you great presentations like this. And it's just a pretty cool shirt, right? That's pretty neat. Until next time, everybody.
Thank you all.
Keep an eye on that James Webb Space Telescope website. And thank you, Stephanie. Thank you, Peter, for hanging out in the chat and all the great links and information that you shared with us as well. We'll see you all again real soon. Bye, everybody.
Bye. Thanks again.